Good morning. My name is Peter O'Donnell. I'm a Principal Solutions Architect with Amazon Web Services. I've been here for about 7.5 years, covering some of our largest, most challenging customers. And what we've learned from customers is that encryption as a root form of the type of trust for not only security, but assurance that your data is well protected, that you understand the context in which encryption keys may be used to access that data, is of course of fundamental and profound importance to our customers. So what are we going to talk about today when we say cryptography for the long term? We're going to talk about encryption in motion very quickly, because largely a lot of that is out of your control. But we're going to talk about where you can make decisions to raise the bar on how encryption in motion works. We're going to talk about secrets management. And you may think, well, secrets management, is that a cryptography topic? Well, for us it is. The Secrets Manager service that you use and consume is actually created by the same service team that powers the credentials that we use internally at AWS. We're going to talk about CloudHSM, our dedicated standalone HSM product that gives you a lot of control, but it also gives you a lot of responsibility, which you may not want. I'm going to help you understand when you should choose it, and largely, when you should not. KMS is our flagship key management service, and that is the right choice for where to store and manage your cryptography in terms of key management for encryption at rest, and for application integration, where you might be doing field-level encryption. We have a beautiful encryption SDK that Matt is going to get into. We're going to talk about XKS. This is a new choice for customers. We'll get into that in a little bit. We're going to talk to you about what's happening with post-quantum. Matt is one of our chief cryptographers, been very close to where we're going with post-quantum. There's a lot of interesting stuff there. And then finally, a little bit about the very far future for cryptographic computing. So let's talk about TLS. TLS is understood kind of along two dimensions, and they're not really the same. One dimension is the version of TLS. This is the implementation of the protocol, how a handshake and a session is established in the first place. But there's also another dimension to understanding TLS, and this is this idea of cipher suites. So, okay, the protocol is a little bit, okay, you go first, and then you do something, then I'm going to come back, then I'll do something. But the cipher suite is a very interesting dimension, because the cipher suite chooses the cryptographic protocol and algorithms and implementations of those algorithms that are used to support some big ideas. Establishing identity, exchanging key material, or at least agreeing on key material. And this idea of making smart choices here, customers often come to us and say, well, why do you still support X? Well, because we're in the business of compatibility. And the truth is that it's the client computer, the client that actually chooses what to use when protecting encryption in motion. And the server says, well, this is what is available. And so if you control your own clients, it doesn't matter if we accept older TLS versions, because your clients can choose a higher version. And this idea of the cipher suite in particular, TLS 1.2 and earlier, is across these four dimensions. And what's interesting about TLS 1.3 is that they've wrapped some of those dimensions. They're no longer optional. So when we talk about key agreement, it used to be that we would use asymmetric to share a symmetric key. And that's great, unless your adversary is capturing all that traffic and pops your private key that was used to protect the symmetric key. So in TLS 1.3, it demands something called perfect forward secrecy, where the symmetric key used for the bulk encryption of the actual data in the session is never sent over the wire. So change is coming. We are uplifting our minimum version across all of AWS next year. And you should prepare for this. It is probably the case that this is a no-op. It is probably the case that all of your clients are already good at choosing TLS 1.2. We've already done this for the FIPS-validated endpoints here in the United States. So if you have FedRAMP workloads and you can choose to use our FIPS endpoints in Virginia and Oregon, Virginia, Oregon, and California and Ohio, those endpoints are already validated. And number one, they're validated by the FIPS, but number two, they already require TLS 1.2. But when you need to go deeper, and maybe you operate at scale, and maybe you have legacy clients that you can't update, really old .NET, really old web browsers maybe, then you need to go look and see if your clients are negotiating anything lower than TLS 1.2. And most of our services support very interesting details in CloudTrail. And that detail tells you what TLS version is being used. And so hopefully everybody here at a 400 level talk understands and recognizes a CloudTrail event entry. And what you'll see here is that, again, most, not all, but most of the services, certainly the ones that are of the greatest relevance to our customers, support this. And you can go deeper and understand not only the TLS version being selected by the client, but this user agent string is really important. At Amazon, we talk very much about this idea of trying to make multiple problems the same problem. And in fact, your problem will not be, my clients don't support TLS 1.2. Fundamentally, your problem is, my software is old. And at hyperscale, you can't just maybe grep your CloudTrail. And so we have a lot of really powerful services to understand this at great scale. So if you're throwing off gigabytes of CloudTrail, a grep is probably not your best idea, and maybe you could hit it with some partner products, lots of really wonderful log ag in the world. And we, of course, have some really great services that do this as well. So let's talk about what about your own endpoints on AWS. Everything I was just describing is where we provide the TLS termination when you call our APIs. But many of you, perhaps all of you, are publishing your own TLS endpoints, whether with Application Load Balancer, API Gateway, or even CloudFront. And for those services where you are terminating your TLS for your purposes, we give you some control. This is known as security policies, and we publish them. They're canned. And what the security policies basically control is that cipher suite idea. Which encryption algorithms, which implementations of those crypto algorithms, call it modes, and which key sizes are acceptable. Now you may think, well, why do you have a range of cipher suites? Why do you have a range of security policies? Aren't you telling me that one is better than the other? No, I am not. What I will point to is that the more restrictive ones and the less restrictive ones still support the same stuff. Because again, it is the client that chooses amongst this. But you may have your own requirements. You may have interpretations of your own requirements where you need to raise the bar. And if you can do that safely, cool, pick the most restrictive one. But be sure, it'd be a dumb way to take an outage. Be sure that your clients are compatible, but if they are, absolutely, raise the bar, right? Go to all PFS all the time. Go to TLS 1.3 all the time, sure. Really, really powerful stuff. Now, in a compliance context, sometimes the threat model is not the important part. But if you're security engineers and you're security people, and you can have a reasoned conversation with your compliance people, which I hope is possible, then you can have a broader conversation about what is the threat model. If you're operating entirely within VPC, cipher suite selection is maybe not that important because all of that traffic is within a trusted boundary in the first place. and there is no spanning port, and there is no nation-state actor looking at all of this. But if you're distributing things over the public internet, maybe you do have nation-state challenges or determined threat actor problems. Lord knows a lot of our customers do. And for those cases, please do consider the threat model. And for those very high-risk connections, sure, a more restrictive cipher suite, a more restrictive security policy makes a lot of sense. So, what are we doing in this area? Part of the theme today is that rigor, that we are really into protecting our customers' data. We're really into establishing a lot of facts and a lot of continuous innovation so that our customers can do two things. Number one, be secure. And number two, form opinions that you are in fact secure. Form opinions in a compliance context. Form opinions in a legal context. Form opinions in simply trusting some bookseller from Seattle to run your computer systems for you. And S2N is a great example of this. Following Heartbleed, we kind of took a look at OpenSSL, and OpenSSL is amazing. It's the workhorse of the internet here. But we saw an opportunity to reinvent. We saw an opportunity to re-implement the nature of the TLS protocol from scratch. And we did it with a couple of very interesting design goals. S2N is open source. It's written in a way that can be easily understood both by humans and by machines. And what does it mean to be understood by a machine? Well, this idea of provable security and automated reasoning. We've been able to apply the rigor of turning this into a fancy math problem and establish that it is in fact correct. S2N Quick is even more interesting. If you're familiar with Quick, Quick is a beautiful protocol. It's now known as HTTP3. And we have an implementation for S2N that implements Quick as well. Really, really powerful stuff. And so Quick is also available for you to use if you're terminating your own TLS and you're not using a load balancer, you're not using CloudFront. And maybe you're doing that for very specific reasons. And if we met together, I might challenge that. But if you need to use it, you can also use Quick. So that's encryption in motion. Let's talk about secrets. What is a secret? Well, a secret is a type of credential, traditionally, username and password maybe. But truthfully, a secret could be a lot of different things. You could hold private key material in a secret store. You could hold configuration data in a secret store. And so when you think about, well, where should this live? We built a really nice service that it's otherwise Amazonified. What does that mean? Well, it means you get fine-grained IAM control to it. Secrets Manager creates a namespace. You can grant access to the secrets by that namespace. You can also authorize it using tags, attribute-based access control. And the most important part about Secrets Manager is rotation. Secrets Manager is not a replacement for doing it the bad way. Secrets Manager is an opportunity to do it in a better way. So it may be that today your DBAs are the ones keying in the secret. Well, it's cool that it lives in a trusted repository, but that's a lot of operators who would know or otherwise come into contact with that secret. The promised land here is high velocity secrets rotation. And not just high velocity secrets rotation, but secrets rotation where no operator ever comes into contact with the secret. Just generate a random string, use that as the password, who cares? The computer's the only one that ever sees it. Your operators do not. So Secrets Manager has a new capability where we will automatically replicate a secret for you. More and more customers, especially at hyperscale, especially with civilization critical workloads, are looking at resiliency not just in region, which is where you must start, but not just resiliency in region, but resiliency between regions. And if you're using DynamoDB global tables, if you're using Amazon Aurora global database, that means you're going to have workers both writing and reading from a database in more than one region. And that's cool, it's amazing, but it becomes really hard because now, well, how do I keep everybody in sync? Well, Secrets Manager can do this for you. So if you have an Amazon Aurora global database with a leader in one region and another leader in the other region, and you've got consumers in both regions, they can be consuming the same secret. So it's also true to know that when we protect secrets in Secrets Manager, that by default, and without the option to disable, we are protecting those secrets using KMS. The secrets are never committed to non-volatile storage when they are not wrapped by this key. And so we give you some interesting flexible policy control that you're authorizing not only access to read the secret, you're also authorizing corresponding access to use the encryption key material that is protecting that secret. And again, what I think is really interesting, we try not to just ship our org chart, but I think it's important to know that the team that built this is not just some scrappy team. I mean, we're all some scrappy team, frankly, but the team that built this is the secrets management team for Amazon. The secrets that you don't see, the secrets that we use behind the curtain, is run by this same team. The secrets that come up out of the instance metadata service. The instance metadata service that furnishes credentials automatically to EC2 using instance profiles. That system, the hands-off Secrets Manager, you don't see it, right? But that's where those creds come from. Same team. We take this deadly seriously. We really want you to rotate secrets. And historically, rotating secrets has been dangerous. Best case scenario, it still means shutting down your systems, which might be dangerous on its own, or at least complicated. And so the pattern for rotating secrets can be very different. That you're not just changing the password of the application user. You're going to create a new application user. And for a time, both will have the same entitlement and both will work. And using Secrets Manager and its plugged in, provided out-of-the-box Lambda functions, and we've written all these integrations for RDS, for Redshift, and many more. Plus, we give you a template, so if you're running Sybase on EC2, you can still do it in a clever way. And this idea of rotational velocity is not something you want to start with, but it's something you can build towards. And this pattern of concurrent availability of a secret changes the model. So if you have a fan-out application that is consuming Dynamo, it used to be that you had to manage the secrets very differently. And if you were going to change the password, you had to change it everywhere at once. Not only do you have to change it on the database side, the username and password, but you have to then go update all the application servers. And that really means turning everything off. That stinks. So this idea that we support out of the box is very different. We can create a new user with a new credential and get everybody to start using it, and then turn off the old user. This means two things. Number one, means you can rotate safely. Means you're not breaking the old secret. And number two, it means you can turn the crank on how often you do this. And so maybe today you're doing it once a year or once a quarter. And that's okay. But it probably means operators are coming into contact with it. It probably means there's humans in the loop there. High velocity rotation means a couple of things. It requires that humans are no longer in the loop, and that's awesome anyway. And it also means that you can be doing it daily, because who cares? The hands-off Secrets Manager, where we plumb the credentials into EC2, those things change throughout the day, and you never see them and you never care, because they're always there. And you can do the same thing for RDS. You can do the same thing with Redshift. Very, very powerful. And it transforms the threat model. Because again, you're no longer just rotating it because what if Dave left and he knew the password to the database, so we gotta change it all. But get to a place where Dave never knew the password, where only the computers ever held the secret. So much stronger. And your compliance friends are going to love this. Internal audit is going to think this is a very cool idea. So of course, I mentioned that Secrets Manager is Amazonified, and again, CloudTrail, CloudWatch. We get really good events on all this. AWS Config, with which I hope you're familiar, and if you're not, you need to go learn about it. AWS Config picks up from the event bus. And AWS Config can give you transparency into this phenomena over time. And it's really, really powerful. So let's talk about, we talked about it in motion, we talked about secrets. Let's talk about protecting keys. This is a 400 level talk, so I'm going to move quickly through this because I think you know it. But as it turns out, encrypting data is the easy part. We're going to start with a data encryption key, and we're going to combine it with data. And then what do we get? Well, we get encrypted data, and that's awesome. That's easy. The hard part is, what do I do with that data key? And the right answer is we're going to encrypt that key too. When you encrypt a key, the term of art is wrapping like a present. So we're going to combine that data key with yet another key, the KMS key. We're going to start calling that the root key for this discussion. And when we protect the data key with the root key, we then get an encrypted data key. And where will we store the encrypted data key? Well, as it turns out, the right pattern is to store it together with the encrypted data. This is how S3 works. This is how EBS works. We store the wrapped data encryption key alongside the ciphered data itself. And in the future, when you need to access the data, we unwrap the data encryption key securely within the KMS HSM. We return the clear key to the service so it can use it to provide you access to the data. But okay, it's turtles all the way down. Like, what are we going to do with the KMS key? Well, the right answer is, and where should we use it? When the right answer is, we're going to use it in the HSM. But the HSMs, of course, have finite memory, and you probably wouldn't want us to like keep your keys in memory indefinitely, and we don't. When you need to use your encryption key material, we pull it from storage. It's not in the HSM. So how can it be safe in storage? Well, we're going to wrap the KMS key too with yet another key. And we get encrypted root keys. Now here is where we take over. Part of the design and implementation of KMS and our commitment to durability and security means that when we store these things in non-volatile storage, they're always wrapped at all times by yet another key. And that key moves at a pretty high velocity. And then the question you may have is, well, what are you going to do with that key? And surprise, we're going to wrap it too. So the KMS key hierarchy is very interesting. What protects your data? Data encryption key. What protects your DEX? The root key in KMS. And that's where you do policy enforcement. Lots of clever things you can do on the policy document for the key. Takes a resource policy, like a lot of things here at AWS. And then the rest of it we take care of, because we're a managed service and we're really good at this. And we ensure the durability and the security and the availability of all of this key material, because you need it. And if it hiccuped, you couldn't maybe access your data, which is maybe worse than the computer dying. So this idea then, to use keys securely in HSM, we want you to use KMS. It is low cost, it is hyperscale, and you've hired us to do a lot of the really hard part. Some customers look at CloudHSM. So why CloudHSM? Well, CloudHSM has some interesting characteristics that might meet your actual use cases. If you have software that is built with PKCS 11, you still need an HSM that speaks PKCS 11. That's CloudHSM. A lot of customers came to CloudHSM because they wanted level 3 for the FIPS program. FIPS 140-2 is the name of the program, the standard. Level 3 is above level 2, but below level 4. And maybe your regulator, maybe your auditor, maybe your downstream customer demands level 3. All right. You can use CloudHSM for that. So CloudHSM implies a lot of interesting things. It is a rock solid product, but it comes with a lot of trade-offs. Pardon me. And because of the additional control, and control is a little squishy term because you completely have control of your keys in KMS, you're just hiring us to do the hard part. But in CloudHSM, it's somewhat separate from the cloud. That CloudHSM has its own way of talking to it. It's not APIs. We give you APIs for the control plane to like launch the thing in the first place, but when you interact with it, you're not talking to us, you're talking to it. And that's important for some customers. But control implies responsibility. We scale KMS transparently to you. And if you know you want to launch something that's going to require 100,000 requests per second, which is a lot, you can call us and we can do it. But in CloudHSM, you have to do all that stuff. You are responsible for the health and the maintenance of this thing. You are responsible for scaling it. And that maybe not is something you really want to get in the business of. So going back to this idea of FIPS 142 level 3, one thing that's interesting is that if you wanted to use KMS, but you needed level 3, we introduced this idea called custom key store. And custom key store allows you to have the top half of KMS with all of its clever API integrations, simple RESTful interface, its tight integrations with AWS managed services. But you didn't love the idea of a multi-tenant HSM, maybe because somebody was uncomfortable, I don't know. And you could definitely talk to us, we can make you comfortable, or at least give you information so that you can become comfortable. But some customers really wanted their own HSM. All right, so that's custom key store. But the regular key store for KMS is awesome. So custom key store, single tenant, it's in your thing, and it is validated at FIPS 140-2 level 3. But the truth is that KMS HSMs are really great. They're awesome. They have been submitted for FIPS 142 level 3. And as of last year, they have been submitted for FIPS 140-3. What is -3? Well, it's the new standard. NIST is effectively deprecated -2. They're no longer taking submissions for -2. And we will be one of the first providers to deliver a FIPS 140-3 managed HSM product at level 3 for KMS. Now, we're working closely with NIST. We expect that letter in the future. But the fleet of hardware that exists today changed. We rolled out brand new HSMs while you were sleeping without taking downtime. And the modules that are out there today are tested and submitted for 140-3 level 3. And so if you're thinking to yourself, well, I know I needed custom key store, but then you maybe had scaling challenges with it. And maybe the only reason you went to custom key store was for the level 3. Well, I have really good news. Maybe you can transition off that thing and just use regular KMS. And these devices are very serious. I tell customers that KMS is a very serious service built by very serious people to meet the requirements of very serious customers, from financial services to government to national defense to healthcare and life science. We know that protecting your data is critical, and we obsess over getting this right. But despite KMS HSMs being great, our friends in Europe understand regulations and understand expectations in new and changing ways. And if you need to hold the key material in your own facility, I'm pleased to tell you that this week we announced the general availability of a new model called the external key store. And like the custom key store, where you get the benefit and fungibility and flexibility of KMS with an HSM that's in your VPC, that's a single tenant, XKS uses that same similar model. It's still a KMS key. It still tightly integrates with SageMaker, with S3, with Dynamo, with RDS. But instead of the KMS HSMs, And instead of the custom key store CloudHSM, you can now use an HSM in your own facility to hold key material and to process cryptographic transactions against that key material. The pattern here is pretty interesting. We launch a proxy. We give you a proxy. We've written one, comes out of the box. It's written in Rust, it's pretty nice. And the purpose of that proxy is so that the proxy can talk to your HSM in its HSM vendor-specific way, but the proxy talks with us in kind of a more uniform way. This comes with some really big trade-offs. This means that if the link between the cloud and your on-prem HSM hiccups, forget it breaking. If it breaks, obviously, everything is over. But even if there's a latency spike, it could be very, very serious consequences for that. So we want you to be very deliberate and thoughtful about whether or not you ever use this thing. Frankly, I kind of don't want you to. I want you to receive the benefit of our massively scaled, hyper-durable, hyper-performant HSM fleet. But if your auditors and your leaders understand their requirements in a way that suggests that you must own the key material in your own building, we built it. Now, when we did this design, and we knew, okay, we're going to take a lot of dependency now on customer HSMs. This also means that the security and integrity of your data, particularly your cipher data now, is entirely dependent on the correctness of the HSMs in your own facility. And that's probably an okay bet, right? We have lots of great vendors. You're probably using a lot of great partners. You can probably trust their stuff. I mean, it's normal. But it's still a pretty big bet. And so again, like Quick, taking it as a signal of our dedication and obsession, we did some interesting things when we implemented XKS. And what we implemented here, I described earlier this pattern of envelope encryption. Well, as it turns out, if we just send the clear data to the HSM, and your HSM, and then you wrap it, and you bring it back, and it comes back, if you wrap it poorly, then it puts the security of all of your data at risk. Because we don't control that thing, which is, arguably the punchline of the service. We don't control that thing. And so our solution here is if you're going to have all this data entirely dependent on a root key outside of AWS, we kind of didn't feel super comfortable with that model. Because again, we care gravely about the security and integrity of your data. So when we take all this data, the choice to make it entirely rooted in the external key store, we wondered if that could be better. And we figured out a really simple and elegant way to do this. And what we do is we actually use a double envelope. So I mentioned earlier that the root key protects your data encryption keys. And now with XKS, with the root key in your own facility, how could we raise the bar on making sure that thing is safe? And the way we did it is with an extra envelope. So when we looked at that pattern before, about a data key being protected with a root key, we introduced a key in the middle. The data key plus a KMS key, then wrapped with the outer envelope of your own HSM. It still requires completely that your external key store be available to do this unwrap. Having this double envelope changes nothing about the security model from your perspective. What it does mean is that if your HSM fouls up its source of entropy and is ultimately weak, which is very unlikely, but corner cases, that even if the outer envelope were to fail or be susceptible to a cryptanalytic attack, that inner envelope, we know, will help. And so again, this idea of rigor, that we have obsessed over protecting your data by building services. We have obsessed over our own services by iterating again and again. With the latest generation of HSMs in the KMS fleet, we're bringing higher levels of compliance and trust than we've ever had before. And customers really like this stuff. We are unrelenting in our focus on innovation here. Again, we are really serious people doing really serious stuff for really serious customers. But I'd like for you to have an opportunity to go deeper on this. What are we doing with the Encryption SDK to make it extremely robust, such that it's simple for you to use, but rock solid under the hood? What are we doing for post-quantum to protect against a possible future of a sufficiently powerful quantum computer rendering not so great certain types of asymmetric algorithms? And what are we doing for the future of cryptographic computing? And with that, I'd like to bring up to the stage my friend Matt Campagna, Senior Principal Engineer, one of our chief cryptographers here at AWS. Matt.
Thank you, Peter. Great. I work with a team of cryptographers, and we're focused on trying to make our tools to a standard sort of security across AWS. So we're responsible for the design and analysis of all the cryptographic engineering that's occurring. And today I'll go a little deeper into some of these concepts that Peter introduced, including how we're securing data at rest, data in transit, and then data in use. So Peter introduced envelope encryption, the importance of getting that right. I'm going to go a little deeper into the AWS Encryption SDK, which is our way of allowing our customers to simply get that envelope encryption using KMS. And I'll go through three specific use cases that we've heard from our customers and some of the engineering that we did to provide that. The first is the simple case of just encrypting one plain text to a customer managed key. So the first thing we do is we generate an ephemeral signing key. And we bind that public key as the additional authentication data in the encryption context to a call to the KMS under your customer managed key to the generate data key call. And we get back this data key and this ciphertext value. And then we derive another key and a commit value for that plain text using a random message ID. And this may seem strange at first, and it's not completely necessary for this simple use case, but as I go through the additional use cases, you'll see the purpose of these values. And then we use authenticated encryption to encrypt that plain text, resulting in the ciphertext and tag. And then we form sort of the body of that one storage unit of the encryption SDK ciphertext, which includes that envelope encrypted data key in the ciphertext, the message ID in the public key, and then the ciphertext and tag. And then we sign that with that private key. And what that signature is doing is it's ensuring we're extending the policy that you have over your customer managed key. So if you have that key and it says Alice can encrypt, but Bob and Chelsea can only decrypt, well, Bob and Chelsea gets the data key, but they have no capability of getting the private key associated with the necessary public key that's bound to the ciphertext. And it prevents them from Chelsea sending a message to Bob that Bob can't distinguish didn't come from Alice. So it's our way of extending your customer managed key policy over the encryption ciphertext. The next use case is suppose you want to encrypt 1 million plain texts under the same CMK. Well, the first two steps remain the same. You generate an ephemeral signing key, you bind that public key to your data key and ciphertext, and then for each message that you want to encrypt, you generate a random message ID value and do a key derivation function to get your encryption key K and this commit value, and then you encrypt each ciphertext or each plain text to get a new ciphertext and tag, and then you sign it as before. So now I can encrypt 1 million messages with a single KMS call. That's a big savings. You know, it's 25, 30 milliseconds to make a KMS call. You know, if you're encrypting millions, that adds up. There's also the API cost for each time you call KMS. So the last part in here is this commit value that I haven't really gotten into. And that's for this other use case. Suppose I want to encrypt a message, and I'm encrypting it to multiple customer-managed keys. So I have a customer-managed key for Bob and one for Chelsea, and I'm sending the same plain text to Bob and Chelsea. So I generate, first two steps remain the same. I create an ephemeral signing key pair. I bind that public key to the first generate data key call, and then I bind that public key again to a call to encrypt that key under the second customer-managed key. Perform the same key derivation function, get a ciphertext tag from the authenticated encryption, and sign that. So what could go wrong? And really to understand what could go wrong is you have to look a little deeper into how authenticated encryption works and what were the requirements for authenticated encryption. So if you haven't seen authenticated encryption, it sort of does two things. It'll take a plain text and your key to produce a ciphertext and tag. The encrypted message is the ciphertext, and the tag is a message authentication code. On a successful decrypt, put in the key, put in the ciphertext and tag, and you get out two pieces of information on a successful decrypt. First, you get the plain text. What was the message? The other thing you get is message authentication, that only the person who had this key could have sent this message. It's designed, hopefully these colors come out okay, but there's slight changes in the ciphertext or slight changes in the tag represented by the yellow text. If you call decrypt, then you get an invalid response from the decryption. So what happens when the key changes? And well, that really is not determined. That wasn't part of the design requirement for authenticated encryption. And to get that, you need this property called key commitment. What you could do is you could take two keys, K and K prime, and generate a ciphertext and tag that decrypts to two different messages. And this should be surprising. I think it was largely unexpected, I think, that people found these issues with the authenticated encryption schemes. What that means is without this without this commit value, somebody could, a user of the toolkit could generate one encryption ciphertext signed ciphertext value and put in there two different data keys bound to the same public key. They're going to run a KDF to get two different Ks, K and K prime, that will decrypt the ciphertext to two different values, plain text and other text here. And that would be confusing. Now, oddly enough, this doesn't violate the properties of authenticated encryption. Only somebody with access to K and K prime could have sent this message. It's an intentional thing that the sender is doing. But if Bob and Chelsea are downloading the same ciphertext from a web server, they have a reasonable expectation that that's going to decrypt to the same value. So this commit value comes out of the key derivation function. And the key derivation function is operating like a pseudo-random function, meaning that you can't really choose the output. Even given the input or being able to control the input, you don't get to choose the output. It's roughly random. That's why it makes a good key. So it's computationally infeasible to select two data keys that are going to, when you run the key derivation function, you'll wind up with two commit values. So when you're doing the decrypt, you're also validating that the commit value is the same and that the key has been committed. And so both Bob and Chelsea, when they do this decrypt, when they check the commit value, they've also verified that they're using the same key to decrypt. So if the decrypts properly, they're getting the same message. So to find out more about this, if you're doing encryption with KMS and you're doing envelope encryption, this is the tool that we recommend our customers use. It's the tool we use internally. And more details about the key commitment and the release of the SDK that does this can be found on this blog post. The next topic I was going to go through, Peter had the PQ hybrid key establishment. I'll go into that in some details and why we're deploying it today. So as cryptographers, when we think about people communicating over two endpoints, we assume that there's an adversary in the middle. And they can read, modify, remove, delete that data as it goes across the network. So we build a lot of redundancy to deal with the deletion. To deal with the reading and modification, we use modern public key protocols like TLS to make sure that doesn't happen. But there's still this, they can still record this data and hold on to it and wait for maybe a new capability to arise, a new unknown, previously unknown cryptanalytic attack or some other technology. And one of those technologies that we're looking at and investing in is quantum computing. So quantum computing is fundamentally different than classical computing. The basic storage unit of a quantum computing is a qubit. And unlike a classical bit that can hold either a 0 or a 1 at a single time, a qubit can hold both the values 0 and 1 at the same time. So a register of 3 classical bits can hold 1 of 8 possible values. A register of 3 qubits can hold all 8 values at once. And as you increase the number of qubits you can maintain in a superposition state, you get an exponential speed up for certain algorithms. Not all algorithms are amenable to running on a quantum computer. They have special properties. And as luck would have it, there is one such algorithm that breaks the public key systems that we use today. So there's Shor's algorithm, which breaks the public key systems that we're using today based on being able to solve the discrete log problem and integer factorization. So there's a lot of work going on in the industry to make sure that when the time comes, we'll be prepared. So the development of a large-scale quantum computer is still a ways out. There's a significant amount of research and development that the physicists have to overcome to be able to build a large-scale quantum computer. And we have the time now to carefully augment the security we're using today with new post-quantum algorithms. But developing new algorithms takes time, measured in roughly a decade. NIST has been working for the last 6 years on the post-quantum cryptography standardization process. They just held their 4th workshop this week. They've selected one algorithm for standardization for key encapsulation called Kyber. We've been participating in that NIST process for the last 6 years. We've also been participating in ETSI, the European Telecommunications Standards Institute, Quantum Safe Cryptography Technical Committee, for the last 9 years. And we've been focused on developing a hybrid key establishment scheme that I'll go into a little more detail as sort of the underpinnings of what we're putting into the protocols. So we have a specification or a proposal within the Internet Engineering Task Force. That's where roughly all the internet protocols are coming from. So there's a PQ TLS specification there, as well as a PQ SSH specification. And finally, we're implementing these things. We've put Kyber into our S2N TLS. It's in the main line of that source code. We're in the process of moving all those post-quantum algorithms into our libcrypto library. And finally, it's available in our SDK. So how does elliptic curve work? You start with a base parameter G. You mix into it a private value D. You send that new color paint over to Bob. Bob starts with the same can of paint, mixes in its private key, K, gets a new color, and exchanges those back to Alice. Now Alice and Bob have the same value, have the exchange cans of paint. They mix in their secret color, and they arrive at the same secret value. And they use that to encrypt the channel. So almost all the modern protocols operate in that fashion. Oops. So post-quantum hybrid is we're going to do a key encapsulation mechanism with the same communication channel as the elliptic curve one. So a key encapsulation mechanism works a lot like you can think of the secret key is a combination to a safe. The public key is the open safe. Alice sends that safe over to Bob. Bob starts the key encapsulation mechanism, gets a shared secret, closes the safe, sends it back over, and Alice opens up that safe to get this shared secret. They mix in the color paint, and they encrypt the channel using the combination of those two secrets. Really, they do a key derivation function over that and then encrypt the channel. And Eve, who gets to see all these public values, doesn't learn anything about the secrets being used, in particular, the SK, the shared secret, or this magic can of paint, DKG. So we've implemented PQ hybrid key exchanges. It's been available for 2 or 3 years now in our S2N TLS implementation, and we've deployed it. So it's available today on our most secure services, the Key Management Service, Secrets Manager, and ACM, our certificate management. We're in the process, as I said, of taking over our own libcrypto library. So when we did S2N, we essentially rewrote the entire TLS layer. We're doing the same to sort of take control over the underlying crypto library as well. We started with boring SSL, and we're committed to making sure that we're adding the same sort of security assurances that we did to S2N to the libcrypto library. So we have a FIPS. The library is currently under FIPS evaluation for FIPS 140-3 level 1. And we're providing formal methods to the most commonly used algorithms, the elliptic curve, Diffie-Hellman in particular. And we've been super focused on speed. So our previous FIPS solution was doing elliptic curve Diffie-Hellman at about 356 key establishments per second. The one we put in for FIPS last year can do 17,000. And we've made similar performance improvements to our library for Graviton 2 and Graviton 3. You can go and use this today. It's in our AWS labs on GitHub. You can track what we're doing on the Integrate PQ. That's sort of our working ground of moving these algorithms into the main AWS libcrypto. I'm super excited also to talk about what we're doing in cryptographic computing, in particular, a technology called private set intersection. So our traditional security model has been to provide our customers with access control mechanisms, process isolation, network isolation, your ability to encrypt data to the smallest possible attested boundary, to have assurance that only your code has access to your plain text data using technology like Nitro enclaves. But we're not done there. We can go even further. And we're hearing from customers that they want to do collaborative data analytics with their partners. But they have typically put in security controls for compliance or audit. One of the best ways to prove to an auditor that you're not sharing plain text data is to encrypt it before it leaves your organization. So some of the problems we've heard in this space is you might be a shoe manufacturer and you're buying ads and you want to know how effective are the ads that I'm buying on some publisher's site. The publisher doesn't really want to give you their entire subscriber list, who's watching what ads, or any of the data analytics that they've been collecting. But they both might be willing to share something, right? And in particular, they both would be interested to know how many people who saw the ad bought the shoes, right? So Cleanroom is designed, you may have heard in Adam's keynote, Cleanroom, this technology is designed to run within Cleanroom, called private set intersection. So what customers really want to do with their data, they want to encrypt it on-prem before they send it into a collaborative environment like AWS. They send that data encrypted. Some magic happens that you can still compute over that encrypted data, and you get back out an encrypted data set, and then you decrypt that data. So some of that magic technology is something called private set intersection with data enrichment. The way that works is the fields over which you want to do the join, the user identifier. You're going to tokenize that, represented here by the purple bars. The data that you want to enrich, you're going to encrypt. And then you're going to set up a policy that says sort of the minimum number of records each must contribute, or the maximum number of results that you're willing to return. And then you're going to return that encrypted data set to either the publisher or the company or even a third party. And sometimes it's not even important what's in the data. Oftentimes it's just the count. But it's also good to know maybe the causality, like how long after viewing the ad did they buy the shoe? And it's not just inner joins. You can do all these different joins. You can say, who viewed the ad but didn't buy the shoe? Who bought the shoe that didn't view the ad? Who are the people that on the outside or the outer, full outer join of that? We've heard from a number of other customers similar problems. Hospitals that want to know if they have patients in common with other hospitals, but the way they've implemented HIPAA prevents them from doing that in any meaningful way without a technology like private set intersection. Insurance companies that want to query proprietary databases for better actuarial data. Law enforcement communities that are siloed and not allowed to share plain text data, but want to collaborate in a meaningful fashion. So this work, we have a cryptographic computing page, and we're posting the solutions that we're working on and vending and the products that we're building this into. But we also want to hear from our customers. And there's a contact us on that page that goes directly to the applied scientists that are focused on solving these problems. OK, so finally, I just want to say thank you. It's a great opportunity for me to be able to share some of the cryptographic engineering that we're doing on behalf of our customers. So thank you.